I just wanted to spend half an hour or so talking about visualization on the web. I know this is something that a lot of people are increasingly doing. One of the main messages I want to get across from this is it's not quite as much of a specialist task as it used to be. It's something that's much more within the range of people, even if they don't have a lot of software development or web development experience. And so I'm going to take you through some of the tools and techniques, mostly tools to be honest, that we've come across, and try and pick out some of the strengths and weaknesses and hopefully give you a few tips as to how you might use some of these. So I'm going to try not to make this too listy, but at the end of the day I am going to be going through some lists of tools and libraries you might want to pick up. So just so we're all starting on the same kind of page, why do we want to do visualization, put visualizations on the web at all? Well, firstly, very highly accessible to reach a very wide audience, of course. Also to reach a very wide range of devices. So if you're not into app development and programming for Android and iOS and all the rest of it, you can do quite a lot with web pages if you program them in the right way that will still work nicely on touchscreen and mobile devices. I won't go into too much of that today, but it's something not to be terribly scared of. And if you feel like the mobile world is too fragmented, there's too many devices that you could code for, coding for the web is not a bad way to at least reach some of that audience. From a technical point of view, the web browsers that we use are very powerful platforms in their own right now, much more powerful than they were a few years ago. And that's not just because computers are becoming more powerful, but because the web browser is getting access to more and more of the computer's resources, and the 3D engine within the computer is an obvious example of that. So you can now do very, very powerful things on the web, which you couldn't do until quite recently, and I'll show an example of that. There's also a certain amount of interactivity built in. So the way I think of writing a web application is not so much that you're building an application from scratch, you're almost writing a plugin for a web browser. The web browser is giving you some of the capability already in terms of handling the mouse clicks and handling some of the user interaction, and you're coding within that framework. If you were to develop, for example, desktop applications from scratch, you have to do a lot more work to enable some of that interactivity. So in other words, in some ways, developing for the web can be easier than developing for the desktop these days. Some of the libraries that I'm about to show, and I'm going to be focusing mainly on open source stuff, the capabilities that they have on the web, in many cases, outstrip what you can do on the desktop with equivalent open source libraries. And one of the reasons for that is the first bullet point is that the web is so highly accessible that it's worth people putting a lot of effort into developing good libraries for the web, because they will reach a very wide audience. Whereas these days, trying to code for a desktop application, people are much more reluctant to download and install it on their own machines, and in corporate environments they might not even have permissions to do that. So a lot of the stuff I'm talking about is about creating interactive visualizations, the sort we saw earlier. If all you want to do is display an image, then of course the capabilities of the web are kind of less relevant. It's just a canvas on which you put your image. So there's definitely a lean towards interactive stuff here. And so this talk is really more about practical advice than any kind of best practice. I'm not necessarily saying that there is a best practice set of libraries that you should use, but I'll hopefully give you an introduction to some things you may not have seen before. And again, just for those of you who aren't web programmers, just to bring everyone up to the same level as to what comprises a web-based visualization, what's actually happening. Well, you've normally got at least 3 files to worry about that you've got to write, and in some ways those 3 files together constitute your application or your plugin, which is another way to think about it. So you write your overall structure in HTML, any design and styling you do in cascading style sheets, CSS, but most of the action is in the JavaScript part of this. So all your interaction and behavior you tend to write in this language JavaScript, which many of you will know, some of you may not have touched, but that's what's going on. No matter how the visualization is generated, that's what's going on at some level in your web browser. I'll come later on to the problem of what happens when we've got really large data sets that don't fit nicely into that framework, and you might need some special web server software to do that, but I'll come on to that later. And one of the messages, again, is that a lot of the libraries and tools that I'll mention will do quite a lot of this for you. So you're not necessarily programming this all from scratch, although you certainly can. So I'm going to... those slides seem to have got reversed. I'm not quite sure how that happened. But so I've already covered the first bullet point, so there you go. I'm going to be talking a bit about charting, in other words, just your sort of normal graphs, mapping, because that's particularly important to us in environmental science. I'll talk a little bit about 3D. I'll also talk about how you can avoid JavaScript altogether. So that could be quite important for many of you who just don't want to learn another programming language. And I'm going to talk a bit about some more specialist tools that we might use for larger data or for the sort of scientific data we deal with. So we've already mentioned this more than once today, which is D3, which is a very well-known, very widely used JavaScript library for building all kinds of graphical applications. And it can be, it's become so widely used that people now kind of almost use this as the starting point for generating visualizations. We've done quite a few things in D3 in our own institute, and we saw a really nice example earlier today. Very powerful, very popular. It's relatively low level. So if you go into D3 expecting to find a bar chart function, you probably won't find it unless somebody's written a library over the top. What you're doing is manipulating data and the structure of the web page and the styles at quite a low level. It helps to have some knowledge of scalable vector graphics, which is what it's actually doing in the background. It's creating scalable vector graphic objects, essentially. So I was really blown away by the visualization we saw earlier, and very well done for getting that done in a short period of time, because it's really challenging to come in at the D3 level and build your own visualizations. Generally speaking, I would be starting with one of the libraries that's built on top of D3. So we'll come to that in a minute. So I had a look around on the web to try and find a nice, easy introduction to D3, because a lot of it kind of really gets in at ground level, at a complex level. And I found this website. It's the whole series of slides that take you through D3 from what the concepts are to how you do some interesting things. So this is an interesting point. D3 is not about graphics fundamentally. It's fundamentally about data and the documents that your web browser handles. So you use it as a framework to create your own visualizations. It's not about charts or maps or any particular kind of graphics. So that's where other libraries come in that may be built on top of this. But on the other hand, it is extremely powerful. And if you know exactly what you want to do, and you've got a particular kind of interaction in mind that you might not be able to get from some of the other libraries, then getting in at the lower level can be very powerful. If you've got an Oxford interview coming up in 5 days, and therefore the motivation to learn it. So one of the libraries that's built on top of D3 is called C3, imaginatively titled. You'd sort of think that C3 comes before D3, but in fact the C means charts, I believe. So C3 is a charting library that's built on top of D3 that handles all the stuff that you need to worry about with charting, like plotting lines and axes properly and all that kind of stuff. So that's one thing you can look at. So here we don't need to write D3 code anymore. We write our JavaScript examples. This is the one that we tend to use most, I would say. It's called Highcharts. And I actually can't remember whether this is built on top of D3 or not, but it's a similar kind of idea. With all these charts, by the way, you've probably seen these in action in websites. You've got a certain amount of interactivity that you can kind of hover over the data points and it will show you the data values, and you can maybe zoom into the plots and drag and zoom out, and you have a certain amount of interactivity. This is the one from our experience that I would recommend getting started with. Highcharts, it had quite a low learning curve for us in terms of basic charting, and supports a lot of the kind of interaction that we wanted. One thing to watch with Highcharts is that if you're using this for commercial, if you're using this for commercial purposes, there's a different license than if you're using it for non-commercial purposes. So you may have to sit and scratch your head and read the license agreement to work out whether your use is fair under their license agreement. But it is open source. It's still open source even for the commercial version. It's just that to use it, you might need a commercial license if you're a commercial organisation. I've also used this thing called digraphs a bit, and this has been particularly useful for very, very dense time series or graph data. In my case, I was doing a power spectrum that had 1 million points in it or something like that, and then you want your library to be handling tens of thousands, hundreds of thousands, maybe millions of data points, and this was a library that I found that handled that very, very nicely. I think it came from Google originally, and it's been used for very dense visualizations, things like stock prices over a long period of time, dense time series of temperature, that sort of thing. Yeah, digraphs could be worth looking at for that particular use case. So just give a quick summary. D3 is extremely powerful, but unless you really have to because you've got a specialist use case, I wouldn't necessarily start there. I would start with one of the charting libraries. Highcharts would be my choice, and digraphs could be another one. I'm sure other people with different experiences would make different recommendations, but those would be mine. So now mapping. Lots of us will be creating applications that have got some components of mapping in there, generating interactive maps of some kind. And a lot of us would go to Google Maps for the first, as our first thought there. I would discourage you from doing so. Not because there's anything wrong with it technically necessarily, but because there are open source solutions that will do most of the things that we would want to do with a mapping solution and don't come with another license agreement. If you have Google Maps, if you use Google Maps behind a login and you're not paying Google, technically you're contravening their license agreement. So you want to be avoiding this kind of stuff, and you want to be using the open solutions if you possibly can. For many, many years, the leader in this open source mapping field was OpenLayers, which is kind of the granddaddy, the big daddy of online mapping. And it's a very, very powerful library, very, very powerful. It will talk to lots of different data sources. It will give you lots and lots of capabilities, but it also can be quite hard to get into because it is so very powerful. So I would recommend this, but I think as a starting point, if you're new to this, I would start with this, which is Leaflet, which is a much smaller library. It's a more modern thing. The code is probably a bit easier to read if you need to get down into the code level. It popped up more recently, and for simple use cases, I would say it's easier to use than OpenLayers. So this would be the place I would start, and if you find that you're getting into use cases it doesn't support, then you might want to move to a different library, but that would be my recommendation where to start. It also works very nicely on mobile devices, as probably OpenLayers does as well these days, but you can get very quickly to producing nice maps using Leaflet. So I mentioned earlier this perennial problem of map projections, and one of the problems with all those mapping solutions that I've just mentioned, and pretty much every web mapping solution that's out there, is that the default projection is the dreaded Mercator projection. And that's because of all the reasons I talked about this morning, about it preserving shape and being useful for navigation and all that kind of stuff. But we tend not to want to do that. We really want to be producing our maps in different projections. And here we often get a practical problem, because the people who develop these libraries don't have our use cases of just displaying the data over large regions and over global scale. They don't really care about equal area stuff and things like that. So they don't necessarily make it easy for you to generate maps in different projections. Just to give you an example of, another example of how much this is a problem, this is our first attempt at developing a particular demonstrator for a particular project. You don't really need to know what it is, but this is the Mercator projection. You can see how much Scandinavia is kind of dominating this, this visualization. We really want to switch to an equal area projection. So here is our latest version, which is using an equal area map. You can see that the relative sizes of Scandinavia and Southern Europe are now much more accurate. Aerial statistics were quite important for this application, but it's actually quite a headache to generate web maps in non-Mercator projections. And one of the reasons it's a headache is because you need these background maps here. to contextualize your data. And most background map servers will only serve data in Mercator projection. So you either have to set up your own server for background maps, or you do what we did, and was basically we used the leaflet library with a vector representation of the continent outlines and loaded that vector representation into the website instead. Used leaflet's projection capabilities to reproject the continental boundaries into the projection that we wanted. So we bypassed this problem of not having background maps in the projection we wanted. I've just realised I think I'm hitting the type in mic. Apologies for that, AD. There's probably some explosions on this recording now. So yeah, that would be our top tip for if you want to use alternative projections, is either set up your own background map server or use a vector graphic instead. If you're wondering how to format your data for these kind of applications, then GeoJSON is a pretty good starting point. Maybe also KML, but GeoJSON is probably where it might start for formatting points, lines, polygons, that sort of thing, because most of these libraries will read it. I'll talk a little bit later about raster representations of data, because GeoJSON won't handle those. I would recommend Leaflet as your starting point. OpenLayers is also far more complex. No need to use Google Maps, I think, unless you really have a use case only it can support. I've already said that, and I've covered that too. So these slides will presumably be circulated for your reference. So some of this text is here just so that you can remind yourselves afterwards of what it was I was saying. Sometimes we want to go beyond flat maps, and we can take advantage of what I mentioned earlier, which is the new capabilities of web browsers to deliver 3D graphics and other things by accessing your graphics card. So there's a couple of libraries that I would recommend you have a look at, if you both open source, if you want to do 3D terrain modeling or something like that on the web. We've played with two of them, NASA WebWorld Wind, which is a web version of NASA's World Wind Virtual Globe, and Cesium, which is, I think, comes from AGI, but maybe that's a collaboration. They're both quite similar to the web maps in the sense that they'll read the same kinds of data formats, but they'll give the option to create not only virtual globes like this that you can drag and zoom like Google Earth, but also they can have built into them proper digital terrain models that give you a realistic landscape. It can be quite engaging if you're presenting data like that, sort of a lightweight geovisionary sort of thing. It won't be as powerful as geovisionary necessarily, but it will it might solve some simple use cases. I'd warn you that it can spike your CPU quite strongly. It does make your computer think quite hard sometimes using these kind of libraries, but they are really very impressive and worth a look. I would say if I was to start with one of these, with apologies to my friends at NASA who I've worked with quite closely, I would probably recommend Cesium, just because I think it's a little bit more polished. Documentation is probably a little bit stronger, but both of them are really great libraries, I think. We mentioned point clouds earlier. I've never tried this, but this is an interesting project I came across in my searches around the web. There's a framework called Entwine, which is an open source framework with an open source data format for dealing with massive point clouds like LiDAR data. They split them up into tiles, they call them 3D tiles, so that it can be served efficiently over the web. And that allows you to generate landscapes using Cesium, using these point clouds. I've not tried it myself on my own machine, but I've seen videos and it does look quite impressive. So for those of you into point clouds, you may be interested to know that. And if you really want to get in there and really get into your kind of 3D graphics on the web browser, you can go ahead and learn things like WebGL, which is the web version of OpenGL. Or you can look at some libraries. So there's this library 3JS, which is three-dimensional JavaScript essentially, which has kind of abstracts that away a little bit and gives you a set of libraries for doing all kinds of 3D stuff on the web. So this is a real-time ray tracing application, which is really impressive to see in the web browser. Remembering the first ray tracing I did on my old Atari ST, which took overnight to run. can now be done in real time on a web browser. So that's worth knowing if you really want to get a bit deeper into your 3D graphics. So a lot of these, fortunately or unfortunately, involve you learning some JavaScript, which is a language that not everybody is a huge fan of, let's say. But it's there, it's on the web, it's what people, everyone develops in for the web these days. Just to give you an example, give you a little anecdote, I suppose. This is what's known as the Definitive Guide to JavaScript by O'Reilly. It's over 1,000 pages. And this is JavaScript, the good parts. That was actually written by Douglas Crockford, who many of you know, one of the inventors of JavaScript and a complete guru in the field. That's 172 pages. So they recognise the fact that JavaScript has kind of grown into this huge language that not everybody appreciates, but can encourage poor practice. But if you focus on what Douglas would say was the good parts, then it becomes a bit more of a tractable problem. But let's say you don't want to learn JavaScript at all, and you want to focus on the languages that you already know, which might be, say, Python or R. Does that mean that you can't do any of this web-based visualization at all? Well, the good news is, no, it's not. Otherwise, I wouldn't have introduced it in that way. There are a couple of frameworks I'm familiar with. There may be more as well. In the R world, there's this thing called Shiny, or sometimes known as R Shiny, which is basically a way of taking an R-based visualization that you might have created in RStudio or something like that, and publishing it out as a set of as an interactive web site. And I've seen a few of these applications, they're quite nice. And what it does essentially is to take your R code and automatically generate the HTML, the JavaScript, and the CSS that you need. Gives you a little package that you put on your web server, and off you go. Personally, I'm more in the Python stable, so to speak. There's nothing wrong with R. Python's what I know better. And there's this language that I never really know how to pronounce, bokeh, that does essentially the same thing for Python. So it will take, you can write a bit of Python code and generate a web page with some JavaScript and CSS, and thereby create an interactive website. It's quite easy to do. I did it for the first time a couple of days ago, and it works absolutely fine. And you can see examples of all the sorts of things that you can create with interactivity as well. So those might be worth trying out, at least as a prototyping tool, to get you quickly from where you are at the moment, which might be a set of analysis scripts in Python, to an interactive application that you might want to play with yourself or show to people. If I had a bit more time, I could show you these live, but I think I'll move on. Some of you may be familiar with this thing called Jupyter, or Jupyter Hub. It used to be known as the IPython notebook. It's a little bit like the MATLAB environment that we saw earlier, where you have a mixture of text and diagrams and code in the same document. It renders as a web page, and you can do Python scripting in the web browser, and when you create a plot, the plot pops in the web browser, and you can save the whole thing as either a PDF or an interactive notebook, and it's great because it really encourages collaborative and interactive science. Having done the analysis that you want, you can save the whole thing with all the steps that you went through. Much easier for someone to follow than a monolithic lump of code or a set of algorithms. But this Bokeh interactive visualization stuff dovetails nicely with the Jupyter environment. So although you can't see this here, this plot is actually interactive here. So there's a whole lot of Python code, well, actually not very much, that's gone up there to generate this plot. But this plot is now interactive in terms of hovering, zooming, all the rest of it. A very nice way to work, I think, that I wish I'd had about 10 years ago. Whoops. So most of the libraries that I've shown you so far have been really fairly general purpose, used for data visualization in many, many different fields, not just environmental science. As such, they might not deal with all the use cases that we might have. in environmental science, some of which I mentioned earlier. One limitation is that they're often designed to consume what you might call small to moderate amounts of data. I'm not going to define that exactly, but the sort of data where you might be able to send it all to the web browser or have maybe some kind of simple server. The data tend to be quite simple in nature, either just tables, a bit like an Excel CSV model, static map images, or simple geographic features like points, lines, and polygons. But we tend to have a lot more complex data than that. We have multidimensional data. We don't just care about images of the surface, we care about what's going on in the atmosphere, what's going on in the ocean. We might want to get in a deeper level in the satellite images and process multiple bands. We have in situ observations, and we also have quite complicated semantics in terms of what we're actually modeling here and the nature of the data, which might not be captured by pushing through a simplified format. So one of the main challenges is that the data can get quite big. And by big, I mean you can't really hold all the data in the web browser. You can't send everything over there. So the web server has to provide only portions of data at any one time. And there's two strategies that you can adopt here. There's a kind of static strategy, which is relatively easy, and a dynamic strategy, which is relatively hard. Your static strategy is to split all the data that you've got into pre-existing, pre-generated files that you serve up, maybe one at a time in response to user interaction, so that each file is quite small. That's what's going on in mapping servers, by the way. When you go to Google Maps, it's pre-generated all the maps, and it only sends you the map that you're interested in. So that's quite easy to scale, because all you're doing is serving files from a simple web server. But it's quite inflexible. What happens if you want to slice out some data that's not been previously generated for you, or do some query that wasn't anticipated? So the other end of the spectrum is your dynamic server, where all the data that's generated is generated on the fly in response to the user request. And that gives you as much flexibility as you like, but it's much harder to scale because the server has to be more intelligent, it has to have more power on the server. The server's doing a lot more work in order to serve the user's requests. So things like web map services, web feature services would fall into this kind of dynamic category. And it's why a lot of those services are difficult to sustain and difficult to maintain over long periods of time, because at some point, when your funding runs out and the person who set up the server leaves, you're left with a fairly complicated server to maintain, which will eventually stop working and people won't put it back up again. So if you've got this kind of relatively large data problem, you've got a design decision to make as to whether you're going to go down a kind of static, scalable route or a dynamic, flexible route. We've made our own contribution of software to this kind of field. You may be familiar with web map services, which serve out map images to web browsers and things like that. We've made one of these that serves images of multidimensional data from things like netcdf files, which are files very commonly used in atmospheric science and climate science and this kind of thing. And it's intended to be an intermediary component to build interactive websites on top of. So you've got potentially terabytes of data down here, an interactive web application up there, and a server in the middle. But that's an example of a dynamic server that's doing a lot of work in terms of generating the images for the client, which could be our own client or third-party client. It's built on standards to allow interoperability. But we have a lot of users for this all over the world, but one of the challenges that we do have is how do you keep these servers going when the data get very, very big? And how do you make scalable backends? And you can do it given enough computing resources. You can build servers that scale as much as you like, particularly with cloud computing, but you've got to pay for that in terms of your time and the expertise that you have. So good solution for some cases, but other use cases might not fit it quite so well. In case you want to try this out, we make it available on the web, but also via this OSGeo Live DVD, which is a kind of DVD of open source geospatial software, which provides a good entry point into that kind of software. Ignoring the rainbow colour scales, because this is an old slide, we can, this enables, the software enables you to produce not only just map images, but also different slices through the data, so picking out time series at a point, taking vertical profiles through the ocean, through the atmosphere, transects, this kind of thing. But one of the, I think this is the last thing I'm going to come to. One of the things that we're not taking full advantage of often in web mapping solutions is the fact that browsers are very capable these days. That a lot of those web mapping solutions were designed around the fact that browsers would be very thin clients with not very much capability. They wouldn't be able to handle very much data, and they wouldn't provide all that much interactivity. That's not the case anymore. We can now produce much richer web-based visualizations with a slightly different way of thinking about the technology. And one thing that we might want to do there is, instead of sending pre-generated images into the web browser where there's limited interactivity, is to actually send the data into the web browser, at which point you can use all these other JavaScript libraries that I talked about earlier to interact with it in a much deeper fashion than we've been able to a few years ago. So we discovered that there was a gap. There wasn't really a data format that could handle sending environmental data from the server to the client. And so this is our contribution here, that we developed this data format based on JSON, which is the JavaScript standard kind of data format, which will handle all kinds of environmental data, not only multidimensional gridded data, but non-gridded data like soil moisture profiles, time series at a point, continuous data, categorical data, with support for all the things you might expect in a modern data format, like semantic linkages and internationalization. So what we're trying to do here is encourage people to build web applications built on real data, not just pre-rendered visualizations, and try to make that efficient for quite large data sets. If you're interested, I'd recommend you start with our cookbook, which kind of takes you through the process from the ground level. Just want to show you one example of what we've done with this. This is a land cover map that we developed in collaboration with CEH in a previous project. It's quite high resolution. I think there's something like 7 million data points on this map, showing, you don't need a new for that one, don't worry, showing different kinds of land cover classes derived from satellite data, using a particular classification that's provided here. But not everyone wants to see the data in that classification. Some people are used to their own land cover classifications. So we wanted to provide a little app that would allow people to reclassify the map from one classification scheme to the next. This is actually the same data. It's exactly the same data, just classified using different land cover classes and using a different color scheme. But because we were using this JSON format, we'd sent all the data to the browser. This could be done interactively as part of a browser application. We didn't have to send the data back to the server in order to process it and send us back a different rendering. We could do this live in JavaScript in the browser. And because the browser is quite efficient, handling several million data points interactively was not a problem for even quite an average machine. So there's a video there where you can see it in action. But this was what we wanted to do to prove to ourselves that actually browsers can handle large amounts of data. We can provide quite rich interactive visualizations that we might not have been able to do in the past using quite large data sets. But we also want that to scale, so we're able to split up large multidimensional data sets into these tiles, a bit like web mapping tiles that you get in web mapping environments. So we're only sending the data to the browser that we really need to visualize. So the server basically splits up that big data set into chunks and just it chooses which chunk to serve at a time. And in that way we get some scalability. So I hope this has been a bit of a whistle-stop tour through libraries and tools and technologies and advice, but I hope there's been something in there that you might want to pick up and use. I think the main conclusion that I'd like people to draw is that it's not too hard to generate at least basic web-based visualizations, even if you're not a web programmer, even if you don't know anything about JavaScript and you don't want to know. With a few lines of code in your language of choice, you can create something that's might be good for you to use yourself, or also might be good to share. It doesn't hurt to learn JavaScript. and certainly if you want to get deep into some of these things, it's worth doing. But you don't have to, and even just a cursory knowledge of the main features of JavaScript will get you quite a long way. So a lot of the time what we're trying to do is reuse libraries that are used generally for information visualization in different communities, but sometimes we do have to use particular software for our particular use cases, and I've shown you a couple of examples of that. And I think I'll stop there. Thanks very much indeed.